class because we are Russian County and we're selling the schools around those areas couldn't do one yet since we picked it. So.
Before we start in section 2.7, does anybody have any homework questions? Yes.
2.7
So we didn't even start 2.7, so we won't do those mindscapes till next week, okay? Okay. What was yours?
2.422.
2.422. Do you have different numbers than I? You probably do, don't you?
Yeah.
Okay. So the bank code one had a little different scheme. I'll write down the one that I have and we can look at it. I'm going to look at the bank code number scheme. I don't remember what it was. It was 273 or something like that.
I think it's 739.
Oh, I'm in the wrong section.
739.
739? That was it, 739? Okay. So this needs to end in a number that's 0 mod 10 when we go through the checking process. 739?
Yep.
Thank you. So multiply by 7, by 3, and then by 9. And then repeat that. And then check your arithmetic. Then we add these up. And check your typing in your calculator. So up to here we have 267. We have to add on a multiple of 9 that's going to bring us to something that ends in 0. So to be 0 mod 10 means, since we're doing mod 10, that the sum ends in 0. So 3 would make it end in 0, right? But 3 you can't write as a multiple of 9, so we're not going to pick 3. 13 would make this end in 0. That would be 280, but 13 is not a multiple of 9. 23, no. 33, no. I'm looking for a multiple of 9 that's going to make this end with a 0. 43, 53, 63. So I want to have a 63 here, because then that will end in 0, right? I get $330. So 330 is equivalent to 0 mod 10, because I can take out, let me write that correctly. I can take out 33 multiples of 10 if I have 330, so that's equivalent to 0 mod 10. So that's what I need the sum to come to. So I need 9 times something to equal the 63, and that would be 7. So I just went through looking for numbers that would make this end in a 0 when I added to the 267, until I came to a number that was a multiple of 9. and that was 63. So 7 is the actual number that needs to be in here, because then I'll have 7 times 9 would be the 63. So I had to work a little bit backwards, and I'll just put that in to verify. So you have the idea then how that will work for you, even if yours is a little different? Does anybody have any other questions?
I have one in section 2.6. 2.6.
Okay. So that's to write all of your numbers as a rational number by writing it as a ratio of 2 integers. So the 0.67, I'm actually not, do you have a question on how to use the actual, no. So I can do this on paper?
Yeah.
What's
It's the last one.
the last one? What is your last one?
Mine had 2 instead of 1.
So negative, okay. Okay, so we'll do this with a 2 instead of a 9 so that it matches yours, since I'm not going to be able to submit my answer anyway, since I don't have Adobe Flash on here. So you're looking at the decimal places to the right of the decimal point. So you have 1, 2, 3, 4, 5. So we put the 2 with the negative sign, negative 2 over a 1 with 5 zeros. And then check that in your calculator before you submit it. So we use 5 zeros because there are 5 decimal places to the right of the decimal point. That didn't help. My calculator. I have negative 2 e negative 5. So negative 2 e negative 5 means take the negative 2 and then put 5 decimal places this way. So yeah, same thing. But I guess my calculator wasn't the most helpful for that. Anybody have other questions? Yes.
On the same one,
The first problem?
no, like the next question with the first problem.
The 0.67? Only yours, what is yours? 0.64? So there's 2 decimal places, so we put a 1 with 2 zeros. So you're counting the decimal places to the right of the decimal point, and that's how many zeros should go in the denominator with your 1. That's how you write a decimal in as a fraction. Any other questions? The study group is starting today. It'll be Monday, Wednesdays, and Fridays from 2 to 3 in this Coffin Library 207. That's in the tutoring center. Now, if you're not able to go at that time, but you'd like some help practicing, besides seeing me, you can still make an appointment at the tutoring center. Just stop over in that same Coffin Library second floor and make an appointment with the tutor for Math 100. So online students, I know you can't do that, but you're welcome to email me your work and we can discuss things through email. Yes?
In 2.6, I have a question.
Okay.
The last one.
So the definition of a square root, we wrote at that out, and I talked about it a little bit when we did that review. The definition of a square root is that number that you can multiply times itself and get the radicand, the number under this symbol. So the square root of 2 times the square root of 2 is 2. That's the definition of what a square root of 2 is, the number that you can multiply times itself and get 2. So the question here is, does an irrational number multiplied by an irrational number equal an irrational number? And sometimes it does, and sometimes it doesn't. So the answer is not always. What did I just do? Let's try that again. The answer is not always. I can give you another example where two rational numbers multiply to an irrational. So the square root of 2 times square root of 2 is 2, which is rational, but square root of 2 times square root of 3 is square root of 6, which is irrational. Any other questions?
For the drop boxes, the due date is, the next one is like September 30th.
Oh, I still haven't changed that. So at the end of each class period, I go back to my office, and whatever we got through, that's how I changed the Dropbox.
Okay.
So the next one is for 2.7, right?
Should be.
And we should be able to get to that today. Any other questions? Yes.
So then you said we haven't touched on 2.7. So on Wiley Plus, is that still due on Sunday?
No. So that's the other thing I do at the end of the day is I go and rechange that. So that's why people are asking about 2.7 questions. Thanks for bringing that to my attention. No, 2.7 won't be due until next Sunday, not 2 days from now, but 9 days. Oh wait, I don't know. I don't know yet because today's Wednesday. Now I was thinking it was Friday. Okay.
2.4 and 2.6 are due the 24th.
Yeah.
So then that makes that one be due till either the 24th as well or the 20th.
Whatever we get done on Wednesday for sure is due the following Sunday.
Third would be the following Sunday.
So what we get done today will be due the next Sunday, but in 5 days or whatever. 5 days?
So 2.7 is due on Sunday.
I'm just trying to think that we're not going to get far enough for 2.7 to be due this next Sunday. I'll have to change the due date on that. Okay. Yeah. Okay. That's all we needed. We didn't. All right. Any other questions? Actually, then let's start 2.7. So the author starts with a question in most sections, and this is a section that we start with a question. So the question is there a number between 0.999 ... so the 0.999s go on forever, and the number 1? Write your answer. Yes or no. Or sometimes. That'd be a weird answer, but yeah. Yes?
Yes, because it goes on forever.
So yes, there is a number between 0.9999 and 1. Okay. All right, so hold that thought. Does anybody say no, there is not a number between 0.999 repeating and 1? She says yes? No, I don't think she does. Okay. Okay. So who says I don't know? Somebody says, yeah. Some people say I don't know. Okay, well, we'll come back to that question at the end of the section and see if we can answer it more fully, okay? So your answer is yes, no, or sometimes. We'll see what the answer is. Let's go back and start 2.7 with a little review. Let's talk about rational numbers. Who remembers the definition of a rational number? Even if you don't know the formal definition, what was the way you were thinking of them? Pardon?
Was that the ratio
Yes, yeah. So you see the word ratio in there, so you think of them as fractions. Ratios are fractions. So the formal definition was rational numbers can be written A over B, where A and B are integers, and B is not 0. Well, we saw that not all numbers are rational. In fact, we proved the square root of 2 and the square root of 3 are irrational, not rational. Irrational numbers definition are real numbers which are not rational. Real numbers which are not rational. Well, I'd like you to then go ahead and each of you write down a rational number and an irrational number. So each of you write one down, and then I'm going to go around and pick a few that I haven't, pick a few students that I haven't heard from lately, and ask you to tell me one of those. So everybody write one down, a rational number and an irrational number. Okay, so you can pick on, how about you? What did you pick?
Rational with 2/5.
2/5. Okay, so 2/5 for our first rational. Okay, so that's written as a fraction. And now, how about you? What did you pick?
0.5.
0.5? Okay, so 0.5, and did you decide is that rational or irrational?
It's rational.
Good. 0.5. You can write that as 5/10 or 1/2. Okay, perfect. How about on this side of the room? Okay, so nobody's looking at me on pictures. I can see that. What did you think?
For a rational number?
Either one.
0.25.
0.25. Okay. So rational number 0.25. So 25 1/100ths, which is the same as 1/4. And how about on this side of the room? Does anybody have an irrational number on this side of the room? Yes. What do you have?
7 over 47.
7 over 47. So that would be rational. Okay, so we have fractions and decimals that are ending. Who has an irrational number? Because I'm getting scarce on those. Yes?
The square root of 7.
The square root of 7. Okay, so any square root that's not a perfect square there is going to be irrational. Good. Any other ones? Yes?
Square root of 2?
Square root of 2. Good. Okay. And any other? What's yours? Pi. The most famous irrational number. Okay, these are great. These are great for what we needed. What do you know where pi comes from? Pi comes from the circumference of a circle divided by its diameter. So the circumference is the distance all the way around, and then you divide that by the distance across the diameter and you get pi. It doesn't matter if you have a big circle or a little circle. So that's pretty present and in your face if you're doing geometry, and so all the cultures in the world came across pi and to approximate it to different values. If you get a chance to look up how people in ancient times approximated pi, it's very interesting because clearly you couldn't measure that precisely to find the number of digits of precision that we have without modern tools, but they still had a very good approximation because they used different ways. They used different ways of finding pi. For example, if you take the Egyptians, they did it with ratios. It's very interesting. Okay, so anyway, what we're going to see with these numbers all together make up what's called the real numbers. You see we had one more set of numbers that came out. We're looking at ways of grouping numbers, and the new set that we got today was real numbers. The real numbers are the irrationals and the rationals. Let's put that in parentheses though, because that's not the actual definition of the real numbers. The real numbers definition is all of the numbers on the number line. So all of the numbers on the number line make up the real numbers. So I had you picking out different kinds of real numbers. We can divide the real numbers up in different ways, and one way is to divide them up by the rationals and the irrationals. Have any of you learned enough algebra to learn about I, the imaginary unit I? Who remembers I from algebra? Right? You won't have to use that in this section. So we're not going to look at the imaginary numbers. That means that the real numbers are all the numbers you know except those that have I. Well, let's go ahead and lay these out on the number line. Because what we see on the number line is that the natural numbers lend themselves nicely to being ordered by their size. So I'm going to ask you to lay these real numbers out that you picked on the list up here and put them on the number line where they belong. You can use your calculator if you need to help you figure out where some of these go. It looks like some of these are kind of tiny, so you might want to make large spaces here. And let's just do the positive 2/5 and the negative 2/5. Positive 0.5, negative 0.5, and so on. So remember, as you're going backwards, to the left of 0, you kind of count backwards. So the real numbers are ordered. You get larger as you go to the right. So you have the negative pi a little to the left of negative 3 because negative pi is about negative 3.14. So that's a little bit smaller than negative 3. So negative 2, for example, then, negative 2 is bigger than negative 3, which is kind of weird because positive 2 is smaller than positive 3. Does anybody have any questions on ordering these out? Did anybody use your calculator to find decimal expansions? Like what? Yeah. Anybody else use your calculator? I did. Like, who knows the square root of 7's decimal expansion? I knew it was between 2 and 3, but I didn't know more precision than that. Well, that's because we can take all of our numbers and write them with decimals, right? Whether they're real or, whether they're rational or irrational, you can get their approximate values using your calculator. So let's talk about that a bit. So if you wanted to know pi's calculator's decimal expansion, you could get it to a few decimal places. How long is the decimal expansion of pi? Yeah, it's infinitely long, isn't it? So I'm just going to put ... because my calculator doesn't go to infinity. Well, we talked about how dense, how populous the rational numbers are, and we can see that when we take a look at the number line. So let's take a look at the number line with pi. So we'll look more closely at the number line around pi here. So if I wanted to place pi, which you did on the last number line, you roughly put it a little to the right of the 3. Okay, but we can be a little more precise than that if we had a bigger number line. Now we don't have a bigger number line, so we're just going to expand the number line that we have. So let's think of this as 3.0 and then put tick marks for 3.1, 3.2, 3.3, 4, 5, 6, 7, 8, 9, 4.0. And then 3.14, this is the 3.1, and this is 3.2. So I'm just going to expand that. Now ideally I would have a giant number line that showed the hundredths, but I don't. So I can just blow up the section between 3.1 and 3.2. So here's 3.1. And then that's actually 3.10, and then 3.11, 3.12, 3.13, 3.14, 5, 6, 7, 8, 9, 3.20. Okay, so we can expand that little 1/10 section of the number line to show the hundredths. So now we're looking for 3.14, so 3.10. 3.11, 3.12, 3.13, 3.14, and 3.15. So 3.14 and 3.15 I've marked off on the hundredths, and I can blow that up too, can't I? So I can look more closely to see where pi would fall if I just expand between 3.14 and 3.15. So here's my 3.140, 3.150. So 3.14, 3.141, 2, 3, 4, 5, 6, 7, 8, 9. This time I made the spaces too too big. Okay, there. Fix that. Okay, so 3.140 to 3.150 blown up. So I'm looking for 3.41. Did I say that wrong? 3.14. 3.141. So right here now. And here's 3.142. How long can we keep blowing this up to look for more detail here and where we're placing pi? Yeah, forever. Let's not do that. Let's look at the book instead. Your author does the same thing. If you had 3D glasses, then you could take a look at it in 3 dimensions. If you buy the textbook in a hardback, it does come with 3D glasses. So that's what he did, only he used the square root of 2, and he's blowing up the section of the number line. Because what the author's getting at here is that you can get infinite detail in the number line if you just have a big enough ruler, or if you expand the section that you're interested in. Well, that was the decimal expansion of pi that we were examining. How do the decimal expansion of rational numbers and the decimal expansion of irrational numbers differ? How would the decimal expansion of rational numbers and the decimal expansion of irrational numbers differ? Does anybody know? So one of the fractions you gave us were 7/47. And if you just saw that and it said ... at the end, meaning there's more off the screen, would you know if that was rational or irrational? Nah, I wouldn't. How about this one? If you saw this one, would you know if that was rational or irrational? What would that one be? Anybody know?
Rational.
Yeah, good, rational. And do you happen to know what it is?
Because it goes forever.
Because it goes forever as a... Because this one went forever too, right? But this one goes forever with a repeat. Yeah, with the bar on top. So it's repeating. So the little bar means the 6 is repeating. Okay, so decimal expansions of rational numbers can end in a repeating pattern. Okay, but how about this one? Some of you gave decimals that were rational, like 0.25. How did you know 0.25? How did you know 0.25 was rational? Who gave me that one? Anyone remember? Why do we know 0.25 is rational? Yes. It terminates. Yes, it terminates. So the rational numbers either end in a repeating pattern or terminate. So 0.666 going on forever, or 0.372, 372, 372, ... Or terminating 0.25, 3.73. So that's how you know if you have a rational number. When you look at the decimal expansion, the decimal expansion just terminates. Just ends. You could think of it as ending in a 0, 0.250, or it just has an ending pattern on the right there that is a repeating pattern. Because you could have a pattern that's not repeating that would make an irrational number. So if you have a pattern, it has to be a repeating pattern, something over and over again. So, for example, irrational numbers don't terminate, don't end in a repeating pattern. So here we could write pi down, because you hopefully are familiar with that and realize its decimal expansion goes on and on forever. But for something that doesn't end in a repeating pattern and yet still continues on in a pattern, we'll just go ahead and put 2.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that does have a pattern, but it's not a repeating pattern. Okay? So you distinguish the two. Now we talked about how we could find a fraction between fractions. Let's do that with decimals. I just said let's do that with decimals, and then I wrote fraction. Let's find a decimal. Let's find a decimal between 1.402 and 1.403. In fact, let's be more specific. Let's find a rational decimal between 1.402 and 1.403. Anybody have any suggestions? Anybody? Yes. Pardon? I'm sorry, what?
Like how we did a few days ago, we wrote down the fraction.
Oh, sure, you could do that. Yep, okay. That would be one way to go. That would be a little harder, though. So I'm going to see if there's another way that's, yes?
1.4021.
Okay. Okay, good. So we could go to fractions and then make the fractions have different denominators and find one in between. Or because it's in a decimal, we can put one more digit to the right. So this is 1/10,000th bigger than 1.402, but it's still not as big as 1.403. So this is 1/10,000th bigger than 1.402, but 1.403 is 1/1000th bigger. So not quite big enough. Okay, are there any more? So this is a rational. A rational number between 1.402 and 1.403. Are there any more numbers in there? Any more rational numbers? Okay, what would be an example of one?
Anything between 0.21 and 0.29, or 0.4021 and 209.
Okay, so you're saying we could go like 1.4022 and so on?
Yep.
Okay. Let's do that. Are you okay. That's great. You are working well as a class, putting your minds together, and you found 9 rational numbers between 1.402 and 1.403. Are there any more?
Yes.
What would be another one?
You can add more to it.
Okay. I can add more to it.
Like 1.40291.
Okay. Okay, so you just add one more decimal out. Okay.
You can go on forever.
Forever. Okay, so forever. So how many numbers are there? How many rational numbers? Infinite. Oh, good job. What a great class. Okay. Infinite numbers between 1.402 and 1.403. And these were rational numbers. Because you can just, like you said, you can just make your decimal get longer, and then you're looking at little bitsy tiny bits, as tiny as you like, actually. How about some irrational numbers? So we want it to be bigger than 1.402, but smaller than 1.403. Can anybody suggest an irrational number that falls between 1.402 and 1.403?
1.40234. You can keep going.
Perfect. So this is a irrational number because it doesn't end in a repeating pattern or end. And it's between 1.402 and 1.403. Okay. Okay, so how many irrational numbers are there? Are there more? What would be another irrational one if there is more? You can be as creative as you want in this. I'm not a very creative person, so I usually copy something. For example, I've seen a pattern of ones and zeros. And you can make any sort of pattern you want as long as it's not a repeating pattern and you've made an irrational number. How many does that suggest to you that there are then? How many irrationals between 1.402? Yeah, infinitely many. Yeah. So there's just the tiniest little space, 1/1000th of a unit, and yet there's infinitely many rational numbers in there and infinitely many irrational numbers in there. Now, because you're so used to finding rational numbers and you use those most often, you might think that those are the most common type of number. Here's what we're going to do. We're going to create a number between 1.402 and 1.403, and we're not going to use one of these kind of pattern things that I've been doing. Instead, we're all going to work together to make the number. So I'd like every single person in the room to pick a digit between 0 and 9. So at your desk, write down a digit between 0 and 9. And as we go around the room, I want you to tell me that digit, and we're going to put it on our decimal, and that's how we're going to create our number. So we'll go around like a snake. So we'll start over here and then go to that side. Okay. So what is your digit?
2.
2. Okay.
6.
6.
3.
3.
4.
4.
7.
7.
6.
6.
5.
5.
1.
1.
8.
8.
7.
7.
2.
2.
4.
4.
2.
2.
7.
7.
9.
9. Okay. 9. 6.
6.
6.
3.
3.
4.
4. 3. 3. 4. 8. I totally lost place. Where are we on?
6.
We're on 6? Okay. 6. 0. 2. 8. Okay. Now, right now that's a rational number, but I'm asking you to use your imagination and imagine that you found your digit not by randomly picking it, but by using a dice, a 10-sided dice. So if you had a 10-sided dice and we kept doing this forever, and you were each picking your number using your 10-sided dice. We're creating a number. What is the chance the number is rational? So we're going to keep going on like this forever. Each one of you having your own 10-sided dice to help you pick the digit that you give me when it's your turn. And we're going to do that forever. And tell me, what is the chance that the number that you picked out is rational, that we create that way? Let's go back to our definition. Always in math we go back to our definition, and that's not a bad philosophy in your other areas of life as well. Okay, so we're looking for what is the chance that the number is rational. So that means we're looking at the chance that the decimal expansion either ends. So that would happen if all of you were throwing a 0, right? Forever and ever you all kept throwing zeros. Because then your decimal ends. It ends with 0, 0, 0, 0, 0. That's ending. The other chance would be that it ends in a repeating pattern. So all of you throwing your dice here end up with a repeating pattern. As you each are tossing your dice, and we're doing this forever. So, what would you say the chance is that the number that you would create is rational? What's that?
Pretty slim.
Slim to 0. In fact, it is 0. So the chance of that is 0. Which is really interesting because it means that the irrational numbers are much more populous than the rational numbers. The irrational numbers are much more populous than rational numbers. If we randomly create a number, we're much more likely to create an irrational number if we have it created going on and on in this fashion. Which is an interesting point. You're used to working with rational numbers most likely. You probably use whole numbers a lot and fractions and decimals at end. So those are what you're most used to. And yet what's most common and populous is the irrational numbers. Your author makes a philosophical point about that. He says that in real life, when you hang out with people, you hang out with people that are like you and that you're used to and that are familiar, and you start to think, well, this is how most people are, because that's what you're used to and what's familiar, but it's not necessarily what's most common. So what's familiar is not necessarily what's most common. Okay, let's go ahead and see why must the decimal expansion repeat or end for a rational number. Why must the decimal expansion for a rational number repeat or end? We're going to investigate that by taking a rational number and doing the long division to calculate its decimal expansion. So we're going to take 45 divided by 7. So you're going to need a lot of space here. If you aren't on a full sheet of paper, you're going to need a full sheet of paper because this is what you're going to take a photo of and hand in. And it shouldn't be a photo of the screen. It should be a photo of your work, okay? So we're going to do some long division. Everybody likes that, right? And we're going to do this for 14 decimal places. So remember how you do long division. You take 45 divided by 7, that's 6. Because 6 times 7 is 42. So you put the 6 down over the 5, and then you put 42, because 6 times 7 is 42, and then you subtract. We get 3. Then we put a decimal point. Okay, so there's a decimal point right here for 45, and you put that for the 6. And we put a 0. And we bring down the 0, and we continue on in the same fashion now. So 7 divides into 30 4 times. 4 times 7 is 28. So subtract and get 2. Put a 0 down, bring down the 0. 7 divides into 20 2 times. 2 times 7 is 14. 20 minus 14 is 6. 7 divides into 60 8 times. 8 times 7 is 56. So we subtract. 60 minus 56 is 4. And bring down a 0. 7 divides into 40 5 times. 5 times 7 is 35. Subtract. 40 minus 35 is 5. So we'll bring down a 0 and have 50. 7 divides into 50 7 times. 7 times 7 is 49. 50 minus 49 is 1. So we have a 1 there. We'll put a 0 and bring down the 0. 7 goes into 10 1 time. 1 times 7 is 7. 10 minus 7 is 3. We'll put a 0 and bring down the 0. 7 divides into 30 4 times. 4 times 7 is 28.
What's going to start repeating now, right?
It's going to start repeating. So you're saying I got a 30. So I'm right back here again?
Yep.
Okay. Yeah, you're right. Because then we have to repeat. Okay. So I was going to have you do this longer, but we'll just go ahead and write the repeat down, and you can fill it in later if you want. As long as, oops, now I just kind of whited that out. It repeats as 428571, and I put the repeat first. You would write the repeat second. But can someone tell me why must the decimal expansion begin to repeat? Or end. It could have ended. So at some point, if we'd have got a 0 for the remainder, then it could have ended, right? As long as our remainders were from 1 to 6, then we had to keep going. Can anybody answer why? Why must it? It's from a principle we learned earlier in the semester.
About pigeon.
Yeah, good job, pigeonhole principle. So the only possible remainders are 1 through 6 if you don't get 0. And so as you're going on past 6 decimal places, you're going to eventually have to repeat. Good job figuring that out so quickly. So take a picture of this and upload it, and then you can call this a day. We'll pick up here on Friday where we'll look at some more work in section 2.7.